Hello and welcome to Professor Pedrero's Intro to Eigenvalues and Eigenvectors for Math 2250, Section 6.1. This is one of my favorite areas of all mathematics in linear algebra, is eigenvalues, eigenvectors, and how cool they are. So our objectives for this section are to find, showing our steps, the eigenvalues and eigenvectors of a given square matrix. And so to start off, we want to see what this even has to do with anything. So I want you to find three scalar multiples for each of the following column matrices. So for example, 2, 3, a scalar multiple for that might be 1827. Or we might have -4, -6. So that this is a scalar multiple of the original. So I'm going to pause this while you find some scalar multiples of these guys. Okay, we're back. So you found some scalar multiples. I found several as well, including 0, 0. That is a scalar multiple of this guy. I didn't say they had to be non-zero scalar multiples. I just said scalar multiples. Now let's remember back to how we multiplied matrices. So this would be 1, 2, 3, -4 times 2, 3. And remember, to multiply matrices, we need to multiply rows by columns. So we get 2 plus 6, which is 8, and 6 minus 12, which is a -6. Okay. What about if we do a times -1, 3? Well, if we do that, we're going to get -1 plus 6, which is 5, and -3 minus 12, which is -15. And for here, we get 1, 2, 3, 4 times 2, 1. We will find that we get 2 plus 2, which is 4, and 6 plus 4, which is, wait, hang on. So 2 plus 2 is 4, and 6 plus 4, which is 10. All right. So, oops, I just noticed that should have been a -4. So we get 4 and 6 minus 4. So that should be 6 minus 4, which is 2. Oh, so let me rewrite this a little bit better as 4, 2. So do you know anything special about some of the results here? And why is that special? I'll give you a second to think about that. Okay, so what did you come up with? Well, this case, 8, -6 is not in any way, shape, or form related to 2, 3. But if we look at the output here, 5 and -15, that happens to be, if I do -5 times -1, 3, I would get this guy. So that's kind of interesting. And if you notice here, if I do 2 times the vector 2, 1, I get the vector 4, 2. Okay. So this one, the output was a scalar multiple of the input. And here the output is a scalar multiple of what we of the input. And here it wasn't. So sometimes the matrix multiplication ended up just being a scalar multiple, while other times it didn't. Let's write that down. Okay, so sometimes matrix multiplication is the same as scalar multiplication. And why is this special? Well, scalar multiplication is a lot easier. Okay. Now, I want to switch over to a applet. You can see this on our home page. Let's see. So if you get out of So if we go to our online resources page, there's a couple of links here for eigenvalues and eigenvectors. If we take a look at the Math Insight one, you can play around with him, and I would recommend you do that for a few minutes and see if there's any way that you can make the output, the dotted vector, be a scalar multiple of the input vector. Ooh, looks like it happened when x is 1 and 1/2. Also note that it will do the same thing when our vector is 2, 1. What about this guy? Oh, hey, that looks pretty spiffy. So go ahead and give that a try. Play around with that for a minute. So again, why is this so important? Well, we want to find the situation. So if we have a square matrix A, what column vectors, column matrices can I multiply by and simply have a scalar multiplication of the starting column matrix? Well, the one caveat that I'll say is that the column vector can't be 0, because if I take an A matrix and multiply by the 0 column matrix, I will always get 0. So the one caveat is this x vector, called the eigenvector, can't be 0. But if I can find a situation where the result is a scalar multiple of what we started with, then we call this guy an eigenvector, and the number that he gets multiplied by and the corresponding eigenvalue. So 2, 1 would be an eigenvector with corresponding eigenvalue of 2. And for this matrix, -1, 3 would be an eigenvector with corresponding eigenvalue of -5. So we're going to do a little bit of matrix algebra here, and we're going to talk about AX equals lambda x. If that's true, then AX vector minus the lambda x vector should be the 0 vector. And if I factor out the x, I get the 0 vector. But there's a small problem here. A was an n by n matrix and lambda was a scalar. So to make this be true, I have to multiply by the identity so that I can do a matrix minus a matrix of the same size. And this leads us to what we call, or leads us to our characteristic equation. So we take the determinant of A minus lambda I, where lambda is an unknown thing, unknown number, and then we set that equal to 0 to find our characteristic equation. Let me pause this video and we'll pick up right there in the next.